Good day, good day, good day, good day. Welcome to our third physical science lesson. So today I'll be using the collision theory to relate it to the four factors which we did in the previous video. So if you're new to the channel, so please subscribe and go through our playlist for physical science so that you can go through them in order from the first video until this one. So today I'm going to cover how the collision theory, you can use the collision theory to explain the four factors that we did. And I can assure you this type of question will always be there. Whether you're writing a trial exam, whether it's a June exam or a sub exam or a November exam, they always have this question in your exam. Like every time, they're always going to ask you, use collision theory to explain why something is higher than the other one. So again, once more, please subscribe. So I'm going to go straight to the first factor that we covered before, which is the concentration. So always remember, at a higher concentration, we'll have a higher reaction rate. So at a higher concentration, you'll expect a higher reaction rate. It's a directly proportional relationship. Higher concentration, higher reaction rate. It's a directly proportional relationship. So now, how do we use the collision theory to explain that? Okay, so always remember, at a higher concentration, more reactant will react per unit time. So there'll be, at a higher concentration, there'll be more reactants that will be reacting per unit time. So there'll be more of them at the same time reacting because of a higher concentration. So the level is increased. Therefore, more will also increase. So like you activate someone, you put more of sugar in them, then they start reacting more because they love sugar. So same thing here. The more the concentration, the more the reactant particles will increase per unit time, and also you'll have more particles that will be having activation energy. So because of that, more of them reacting at the same time, we're gonna have more particles having activation energy, and then due to them having activation energy, then you'll get more effective collisions per unit time. So the more they have activation energy, therefore you'll have more effective collisions per unit time, and then that will be your 3 marks, because basically they're going to ask for 3 marks. So this will be your 3 points. First point, more reactant per unit time. Second point, more particles with the EA. Then more effective collisions will occur. Then that will explain why at a higher concentration we've got a higher reaction rate. So those 3 will be your point that you're going to have to use to explain for that question. So now second one, temperature. And again, remember, at a higher temperature, higher reaction rate. It's also a directly proportional relationship. Higher temperature, higher concentration. Higher reaction rate. Higher reaction rate. So they also go together. Higher temperature, higher reaction rate. They go together. It's a directly proportional relationship. So again, how do you use collision theory? This will be us using collision theory to explain that. So using collision theory, remember, at a higher temperature, the reactant particles, they will gain what we call kinetic energy. And then from grade 11, remember, kinetic energy is the energy of movement. Is the EK, is the kinetic energy, is the energy of movement, which is the EK is equals to 1 over 2 mv squared. That was the formula from grade 11. So it's the energy of movement because there's a velocity there, which is v. So that will be v squared. There's a movement because of the v. That will be kinetic energy. So always remember, at a higher temperature, particles gain kinetic energy, and therefore the particles will then move faster, and then because they're moving faster, then they end up having kinetic, so not kinetic energy, activation energy. EA is activation energy. So they end up having activation energy, and then more effective collisions will occur. So again, that will be your marks. First point, particles gain kinetic energy, then the particles will move faster, and are gonna react. And then once they start reacting, they're gonna have the activation energy, and then there'll be more effective collisions. That's when you will expect a higher reaction rate. So the next one, surface area. So I'm gonna focus on the two most common ones. There's also granules, but I'm gonna focus on these two. So remember, with surface area, the smaller the size, remember, the bigger the surface area. So remember, the smaller the size, the bigger the surface area, and therefore the faster the reaction rate. So the smaller, I'm gonna put the arrow showing down. This is the smaller the size. I'm gonna put S. Smaller the size, the bigger the surface area, and also the faster the movement, or the faster the reaction rate. So that will be the order. The smaller the size, the bigger the surface area, and also the faster the reaction rate. So always remember, these two are the most common ones that they're going to ask you, lump or powder. So always remember, powder has the smallest size, lump has the bigger size. So remember, if powder has the smaller size, therefore it will have a bigger surface area. And because powder has a bigger surface area, therefore you'll expect powder to move faster because it has a smaller size. That's the order. Smaller the size, the bigger the surface area, and the faster the movement. So lump has a bigger size. So please don't confuse the two, guys. Lump, bigger size, powder, smaller size. So because they can ask you to compare the two of them. And I've got a graph where I'm going to show you how you're going to compare the two. Let's say I have a graph here. Let's say I'm measuring the mass of a product, or can be anything, can be a mass of anything. So this are my two graphs. Now, the green one, you can see it has got a smaller surface area, which remember are the lumps. The other one has got a bigger surface area. So some people, they tend to get confused now when it's like this, but always remember, lump is the largest size. So always start from the size. Don't just start straight from the surface area. Start from the size. Lump has the largest size. Because lump has the largest size, it will have a lower surface area. So therefore, it will have a smaller movement. That's why the graph is lower. The graph of lump is lower because it has got a bigger size or a smaller surface area. That's why the graph is smaller. So for powder, it is small and has a bigger surface area. That's why the graph is higher. So the graph of lump, it's lower than this, the lump one. I'm gonna put L, and then this one is the powder. So always remember, powder, smaller size, lump, bigger size. So the graph will be different. The graph of powder will show a more curve or a more steeper or more gradient. This line is showing us the gradient or the steeperness, because from here you can see that we've reached equilibrium. At this point, we have reached equilibrium, but from here you can see there's a more gradient, or more the steeper line of powder is high. So therefore, the more the steeper line, the more the reaction rate. And then this is due to powder having the smaller size than lump. That will be you using the surface area to explain this. So now, how do you use collision theory to explain that? So remember, the larger the particle size, therefore the slower the reaction. So the larger the size, therefore the lower the surface area, therefore the lower the reaction rate. So this will result in less particles having the surface area. So therefore, the smaller the sizes they are, the faster the movement, and therefore the more the movement, the more the effective collisions. So for powder, smaller size, more surface area, more particles will react together, and more effective collisions. That'll be for powder. For lump, large surface area, large size, lower surface area, less particles will be around each other or reacting. Therefore, you will expect a less effective collisions. So please guys, don't lose these marks, because they can ask about any of the 4 factors. Most of the people I have sort of like helped before, they tend to struggle a bit with surface area. I hope this will make a difference today. So the last one is the catalyst. That's what I'm going to cover is the catalyst. So always remember, catalyst, it speeds up the reaction rate. We first learned about the catalyst in grade 10 when we're doing about the enzymes. So a catalyst will always speed up the reaction rate, and then it does this through the lowering of the activation energy. So here I'm going to show you how the graph will look like. This will be my normal graph, which remember, okay, I think we'll do the graphs later on. I'm going to show you how they look like. Here you always have a reactant, here you're going to have a product, and then here you will have your activation energy from there to there. So now it's been lowered. This dark line is showing us that our EA, or the activation energy, is being lowered. So it's lowered by the catalyst, and the more it's lowered, then the direction will speed faster. So we've got 2 types of graphs that I think you guys must become aware of. We've got 2 types of graphs that you guys must become aware of. So the first graph that you must know will look like this. Just want to cover this graph shortly. First graph will probably look like this. It will start from there and then it will go down there. So always remember, this will be our reactants here. This will be our product. So always remember, the graph that looks like this, where you've got the reactant higher than the product, we call this graph exothermic. So this graph represents the exothermic reaction. So this graph represents the exothermic reaction. So that graph represents the exothermic reaction. Exothermic. There we are. So the other graph will look like this. Now you can have the reactants here, and then the product will be higher. So let's say the reactants will be here, then the products will be higher. So when the products are higher, we call it the endothermic. This one is the endothermic. The other one is exo. The other one is endothermic. So the 2 graphs that you guys must become aware of. And also remember, the part that we have on top of there is the activated complex. I call it the AC, the activated complex. That's the part we have on top of there. And then here inside we've got the activation energy, which is being shown here. So always remember, we can also relate to the delta H, which is very important for the chemical equilibrium. So delta H for the exothermic reaction will always be negative. So in other words, you can say delta H is less than 0, or it's negative for exothermic reaction. For endo, delta H will be greater than 0 or positive. Will be greater than 0 or positive. That is for endo. So these 2 graphs are very important because they're going to bring them to you guys as well. So you must always know exo, delta H is negative or less than 0. For endo, delta H is greater than 0 or positive. And remember, they can ask you to calculate the EA, they can ask you to calculate the delta H. Remember, the delta H, to get delta H of the reaction, to get the delta H or the heat of reaction, it will always be product minus reactant. The sum of product minus reactant, P minus R. So the value of your product minus the reactant, that will give us the delta H or the heat of reaction. So if delta H is negative, therefore your graph or your reaction is exo. If delta H is positive, your reaction is endo. So yeah, just become aware of such detail. So that will be that for this video. And then I'm going to do another one where I'm going to do some calculations and the Boltzmann curve before I do other sections. So again, once more guys, please subscribe and feel free to ask any questions, and also go through our playlist in that order. And yeah, that will be all for the video. Kori Wangamanda.